Hi everybody, we're back with the sound and decibel. It's chewing a gum. Okay, pardon my drawing. Okay, now it don't look like Elvis. Okay, now initially it forms a small bubble down here. Now imagine you coat this bubble with a layer of butters, nicely coated. Now, the amount of butter you spend coating this balloon of bubble gum, alright, is fixed. Now as it starts to blow, the balloon or the bubble gums get bigger. Now overall the overall butter is still spread evenly across this. Now, does the amount of butter increase? No, the amount of butter is still the same. This is equivalent to energy, alright, or in terms of power rather. But now the what you have here is the butter spreads over a bigger surface area, which means to say that the butter now becomes thinner. Now imagine the sound producing here is very thick, is very loud. As it travels further, it spreads out over a larger area, and the volume of sound should lower, should diminish, attenuate rather. Okay, so what we have here is we want to understand even deeper the sound level and decibel level, basically at the propagation level when the sound is propagating. Now, the loudest sound we encounter rarely exceeds 1 watt per meter square. Wow! Which means to say that, hey, I'm producing, say, an amplifier with 8 watts RMS blasting away, and you're telling me that the loudest sound hardly even hit 1 watt per meter square in intensity? That is true. Alright. Now, inconvenient to use directly this intensity amount. Why is that so? It's because this intensity, remember in our last section, is proportional to amplitude square, which means to say every increase in amplitude is twice. So if we were to plot the graph, literally the graph goes like this. Isn't this the exponential graph that we just discussed much earlier? And to represent this kind of graph is very difficult, because as it starts increase further and further towards the x-axis here, the changes in y is tremendous. Alright, and we will lose details in here as we go higher energy. So usually what scientists will do, they will use the logarithm scale to represent this kind of numeric behavior. So with this, we try to measure sound in logarithmic scale known as decibel. So in fact, decibel is basically a logarithmic scale paired to a reference sound level. That's it. Okay, take note. Later we'll see how this decibel comes into play in a short while. So when we measure sound, we always say it's the sound intensity level, for short SIL. Now, sometimes in a recording studio or whatsoever, you use a sound meter gauge and it give you sound pressure level. Okay, temporarily treat these two as the same first. Then they measure the intensity of sound. In reality, they are not the same. But for understanding, we will treat them temporarily the same. Okay. Now, sound intensity level is the sound intensity expressed in the logarithmic scale, or alright, known as dB. So, which means to say that we know that the mathematical functions earlier is y is equal to e b to the power x. So when we take log y here, and we get x. So basically, this is what we want to do. All right. Okay. So decimal is a measurement between two ratio quantities. It's a dimensional unit like percent. Okay, decibel, first and foremost, you gotta understand that it is a reference unit. Okay, which means that it's a reference unit means that it is not a standard unit. Okay, and how does it work in this case? Now, in fact, I can measure all the heights of all the people in the class using decibel. How is it done is like this. You take an average person, say me. Let me use the bamboo to draw it easier. Alright, so let's line up all the people in the class. Say you have, let me shield my hand a little bit so I can draw much properly. Alright, you have person 1. Pardon for the extra hand, just due to the, alright. And then next you have person here, and an average person here, an average person here, and an average person here. Alright, now you take an average person, or maybe you take the shortest person rather, which is this guy. Maybe he's 1.5 meters, and this person is 1.7 meters. This person is 1.6 meters. This person is 2 meters, and this person is 1.5. Okay, now, or rather maybe I'll just put 1.55 to make sure it's different. Now, this person becomes the reference point. So the height, we put it as height, h naught is 1.5. We use it as a reference. Nobody tells us why. It's just for convenience sake, we choose the shortest person. In fact, we can choose 1.72. All right, but just to make sure that things are easier, we choose the shortest person. Now, then the height of the rest is measured against this guy. Say for example, this guy will be 1.7 against h naught. Okay, now of course in SIL we not just take this, we will take this as what? We will take this, so it will be something like 1.7 over 1.5. Okay, so 1.7 over 1.5. How much would that be? It will be 1.133 recurring. Okay, so it's 1.13 times of h naught. That's what we mean. So this is a ratio property. Does it have a unit? No, because the meter and meter here has already cancelled each other. So there is no, it's dimensionless. That's what it means. Now, second thing is instead of doing this, because remember in sound, our wave is twice the previous one, which is increased folds after folds. So instead of using a linear ratio scale like this, we take the log. So imagine taking a log here. This is log 1.7 over 1 this thing, and the log scale that we take is 10. Okay, so which is equals to log 10, 1.7 over 1.5, and this is, what is this? So, and we take log 10. So this is 0.054. That's what it means. So now let's relate the sound. Sound is also the same thing. Okay, we let one value of sound, which is I think okay, we let 10 to the power of minus 12 be our reference sound. Okay, so let's go back to bamboo. That means the quietest sound that you ever have is 10. Very bad. It's 10 to the power of minus 12 watt per meter square. This is intensity, the quietest that you can have. Any sound that we measure will be referenced to this. So this one we call it the intensity knot. So any sound that comes out here is divided against this reference sound, and we take log 10. Okay, this will give us the decibel. But of course, in our slide here, all right, we need to multiply by the 10 in front. Otherwise, the value becomes 6.0 dB. So we just want to convert it to 10 in this case. All right. So what we have here is we put a 10 here. So this is actually our sound intensity level measured in decibel. Okay, so this is the amount of energy that we have. So you need to know that given a dB, you must know how to find an intensity. And given an intensity, you must know how to find dB. So isn't it the part whereby your logarithm comes into play? Okay, so let's move forward to the lecture. Now, so decibel are useful because they allow even very large or small ratio to be represented within a convenient small amount of numbers. So 0 dB and 60 dB is not 60 times, it's zillion times, alright, it's a lot of times difference. Okay, so this is accomplished by using a logarithm. Now, then next, why use decibel? Because our ear is capable of detecting very large range of sound pressure. The ratio of sound pressure that causes permanent damage to the limit of ear is above a million. Like I said, it's way a lot. So, but you don't measure such a large scale. So you tend to compress the scale in a segmental form. Within 0 to 10 is one scale. Within 10 to 100 is another scale. Within 100 to 1000 is another scale. Within 1000 to 10,000 is another scale. Within 10,000 to 100,000 is another scale. And between 100,000 to 1 million is another scale. So that's what you want this scale to represent, so that you can represent a whole range of sound without having to plot a million points. Okay, so the ratio of sound pressure that causes permanent damage and limit is really above hundreds, millions. That is the threshold of hearing. Okay, now next, the power of the sound, which is I, is directly proportional to the amplitude pressure. Okay, which is amplitude. In this case, the square of the pressure. The pressure here simply means the pressure amplitude. Now the ratio between the maximum to the minimum is above 1 trillion. Wow, that is a great amount of numbers. So that's why we have to use decibel. So in order to deal with this such big range, alright, we try to introduce logarithmic scales so that during the small sections is well represented as it progresses through different segments of ranges. Alright, all the values are well represented. So this is one of the examples that we have. Say for example, the threshold of sound in this case the reference is called is usually known as the threshold of hearing for no sound. That means below 10 to the power minus 12 watts per meter square, there's no way your ear can detect any sound. So we normally use that as a reference point. Okay, so now you have a intensity of sound at 10 to the power minus 6 watt per meter square, which is somewhere in the quiet conversation. Now, can you imagine 10 to the power minus 6 and 10 to the minus 12? How much different is 10 to the power 6? Is 1 million times difference. 1 million times d I naught. That's what it means. So because everything is in exponential scales, that's why we have to use logarithm to represent it. Okay, so can you imagine? It's 10 to the power 6 zeros, guys. Okay, so which means to say if you convert it, it's 60 dB from the quietest sound to a quiet conversation. The intensity increase a million times. Okay, I hope you get what I mean through this. So in order to represent that, we use this formula called SIL 10 log 10 I over I naught to represent all these things inside here. Okay, so far so good. Can. Alright, so for every intensity ratio, there's a corresponding sound level difference in decibel. Now this is a quick and dirty way to approximate the number of dBs based on these things. For every additional dB, alright, the intensity approximately increased by 1.3 times. So can you imagine you just turn on a knob from 60 dB to 61 dB. Alright. Now the sound just don't increase by 1 unit, it increased by 1.3 times what? The previous value. Remember, it's not 1.3 times. It's not 1.3, it's 1.3 times the previous value. Every time you increase by 1 knot, it's 1.3 times. It's like a compound interest. It's add on. Okay. So a sound at 0 dB corresponding to a threshold hearing 10 to the power minus 12. This magic number you have to remember. Okay. So let's take a look at this thing. Ratio of sound intensity to sound levels inside here. So if you have 0 dB difference between two dB, say for example, trumpet, when you measure using the sound gauge is playing at 60 dB and another trumpet playing at 60 dB. So the intensity ratio is definitely the same. So it's 1. So it's alright. So you realize if there's 1 dB difference, say 61, alright, then there is a 1.3 times ratio. If it's 2 dB, it's approximately 1.6. Note that all this value is 1.6. It's by no means the most accurate. In fact, we have to go through some mathematical rigor in order for us to see the actual calculation or the for the additions or the differences in the dB. Okay, so examples of sound intensity level. In air, sound pressure above 85 dB is considered harmful. Alright, so in 95 dB is considered unsafe for prolonged period. Okay, and 120 dB cause an immediate perforation of eardrum. Then perforation means making a hole, tearing. Alright, okay. So window breaks at around 163 dB. Of course, windows break, it all depends on whether the windows is vibrating at the what, at the whether the driving frequency is equal to the natural frequency and causes resonance on the windows as well. Okay, so this is the examples of the sound that we have. So even a library, all right, or empty auditorium is about 30 to 40 dB. There's something like the ambient sound inside here. Whispers about 20 dB, and then what happened? Aircraft engines, 10 meter, 150. All right, it's really unbearable. That's why people working near the airport, they have to wear ear muffles. Okay. Then you have amplified rock music, 110 dB. Wow. So if you are playing rock music all the while for a prolonged period of time, it can be really harmful to your ear. Same goes for workers in the machine shops. It's at 100 dB. So take note of this too. Down here. Alright. Okay, so let's move on. So of course these are useful dB relationship inside here. Okay, but we need some mathematical rigor when we deal with this thing in a short while later. Now this, what it shows here is sound level metals. Okay, so usually they'll put a kind of sponge down here. Alright, So I think to take away some ambient noise or reduce, okay, to make the sound measurement more accurate towards it. So it has three parts. It has a built-in microphone, amplifying and filtering circuits, and you have a readout display to tell what is the sound levels here. Now, the sound meter level usually give you in terms of sound pressure level reading, also in terms of dB. Okay, there's a subtle difference between these two, but at the moment you treat them the same, all right? So that for your easy understanding. Okay, now, so the next step will be the inverse square law. Okay, I'll stop the video here and